In this video, we're going to take a look at the next chapter of the atomic theory. It takes place in the early 1900s, and we're going to take the information that we know about light and energy and add it to the atomic theory in what is now called the quantum theory. So by the end of the lesson today, we'll be able to look at how the contemporary model of the atom is different from Rutherford and Bohr's nuclear model. That's the one that we pretty much ended with. And we'll be able to answer the question if we can explain at least one problem with Rutherford's model and one problem with Bohr's model. If we can explain the debate about whether electrons are particles or waves, and then describe how Heisenberg's uncertainty theory and Schrödinger's probability equation united these opposing theories and helped give us the modern model of the atom. So just a quick review. Remember, if we go all the way back to 400 BCE, we have Democritus, who's a philosopher. He is using logic to determine that matter is made of small indivisible particles called atoms or atomos. And his theory was pretty much dismissed at the time by Aristotle, and it was about 2,000 years before we have a model again of matter that looks like the atom. And that's developed by John Dalton. He is a scientist and a chemistry teacher, and he put together not only theories of other scientists of his time, but his own work showed that matter was made out of small spherical particles called atoms. They were indivisible, and if you had atoms of one type of element, they were alike, and those atoms were different than the atoms of other elements. In the late 1800s, J.J. Thomson was doing experiments with the cathode ray tube and X-rays and discovered electrons. He found that there were particles inside the atom that were negatively charged and much smaller than the atom. And he developed what he called the plum pudding model, or we more recently call it the chocolate chip cookie dough model. And his model said that the atom was still a relatively solid sphere, but that sphere was made up of positively charged matter. Here's the cookie dough. And embedded in that matter were these negative particles called electrons, or the chocolate chips. And then in the early 1900s, Rutherford was doing his gold foil experiment with alpha particles because at the time, radioactivity had been discovered and they were doing experiments with it. And he discovered that the atom is not made up of a sphere of positively charged matter, but rather a very, very densely packed nucleus contained the positive matter, and the electrons occupied what was mostly empty space around the nucleus. And that leads us to Bohr's model. And we've started talking about Bohr's model a little bit, but today you'll see where he came up with his model as we fit it together with the information that we know about electrons and energy and light. And that will take us up to our present modern day model of the atom. All right, so just as the atomic theory continued to develop because there were unanswered questions, there were some unanswered questions about Rutherford's and Bohr's model. And their problems were significant, and according to classic physics, which was studying the behavior of the electrons, we needed to change the model a bit. So Rutherford was not able to explain how the electrons occupy the space around the nucleus. So if we think of Rutherford's model, they were spinning around the nucleus in lots of different orbits or distances from the nucleus. And the orbits were fairly random. It also didn't explain why the electrons are not pulled into the nucleus. In other words, why didn't they spiral into the nucleus? Because the electrons would have been attracted to the positively charged nucleus. And when the negative and positive charge met, it would have caused a tremendous release of energy as the two particles combined and imploded. And it didn't account for the differences in reactivity of the elements. So if the electrons are responsible for the bonding and reactions that occur between atoms, how could you account for the fact that these randomly placed electrons were acting very differently in different types of elements? And so while sodium and chlorine, for example, would act or react in a 1-to-1 ratio, calcium and chlorine would react in a 2-to-1 ratio. And if the electrons were orbiting around the nucleus in very random patterns, there was nothing to explain why these atoms were reacting in such precise ratios. And so Bohr took the information that he had with the light and energy to say, well, the electrons have to be organized around the nucleus in very specific patterns. Because atoms only give off very specific colors of light, it means they absorb very specific amounts of energy. And so they can only be at certain distances away from the nucleus. And those distances away from the nucleus created these spheres within a sphere within a sphere, or orbits, as we would call them in this planetary model. And so according to Bohr, the electrons were acting more like particles, and that those particles could only be revolving around the nucleus in these set orbits. At about the same time, another physicist by the name of Schrödinger said, but we can explain the behavior of electrons if we treat them more like waves. Physics was really good at explaining wave behavior, and the electrons seemed to follow the classical physics model of acting like waves. So, which theory is correct? Is Bohr's work with light and energy and explaining that the electrons are behaving more like particles that exist in certain orbits the correct theory? Or is it Schrödinger's theory that says these electrons are acting like waves? It took a physicist by the name of Heisenberg to unite the two theories. And Heisenberg originally was Team Bohr. He thought that the electrons were behaving like particles. But then he had this revelation that if you want to observe an electron, you have to shine a light on it. In other words, light has to bounce off the electron and into your eye. And in the time that it takes for this ray of light to bounce off the electron into your eye, it has disturbed the electron and caused it to move to a different location. And so we can never know the exact location of an electron because it moves when we observe it. And this is where Schrödinger's equation about waves comes in, because Schrödinger's equation is much more theoretical. In other words, his equation relies upon the idea that we can only know the probability of finding the location of an electron, because if it's behaving like a wave, the wave is forming this orbital shaped or circular shaped pattern around the nucleus. And the electron could be anywhere along that circular path. And it's Heisenberg that says, hey, you're both correct. The electron is behaving like a particle, but we can't know its exact location. And so we have to depend on Schrodinger's theory or equation to predict the probable location of the electron. And so what we end up with is called the quantum model. Again, you can only know the probability of the location of an electron based on Schrodinger's wave equation. And so we have a couple of new terms now. Quantum. The quantum theory is based on the idea that there is a minimum amount of energy that can be gained or lost by an atom. And as we watched the electron circle around the nucleus, we saw that it required a specific or minimum amount of energy to jump from one energy level to another. And as it fell back down, it gave off that photon or quantum of energy in the form of a light wave. And so that photon is a piece of light with one quantum of energy. So it's a point particle that contains a minimum amount of energy. So whatever energy it takes, for example, in hydrogen, for an electron to move from level 2 to level 3, that's a quantum of energy. And as it falls back down to its original energy level 2, it gives off that quantum of energy in the form of a light wave. That hydrogen could also move from energy level 2 to 6. And in that case, the quantum of energy is the amount that it takes to go from level 2 to level 6. And as that electron falls back down to energy level 2, the quantum or minimum amount of energy that's given off is the amount that translates to a wavelength of light that we recognize as a different color. So ground state is the lowest energy level that an electron can occupy. And we know that the electrons will stay as close to the nucleus as possible because of that attractive force of the positive nucleus to the negative electron. But at a certain point, we can't fit any more electrons into that orbit, or we now call it an orbital. If the atom has more than that minimum number of or maximum number of electrons, they have to be located in the next orbital or the next circle out. And for those electrons, that's the ground state. So it's the lowest energy level an electron can occupy. And then we have excited state. So anything above the ground state for an electron would be considered the excited state. So what we have for the modern atomic model is a lot more complex than Bohr's model. We still use Bohr's model because it's easy to draw in 2 dimensions. But according to Schrodinger's equation, at each energy level, we have different shaped orbitals or regions where the electrons can exist. And those regions are based on his equation. So sometimes the region where the electrons can exist looks like this double shaped, kind of dumbbell shaped orbital or area. And sometimes it looks like this one. And we start putting those together at the different energy levels and superimposing them on each other, and the shapes become very complex. So again, we started with Democritus, we moved to John Dalton's theory of the spherical atom. J.J. Thomson added the electrons, Rutherford added the nucleus. Bohr took those electrons and arranged them in what he called orbits at the time. We now call those orbitals. And by combining the particle model and the wave model, what we now call the dual nature of light. We now have the modern theory where we say we can't know the exact location of electrons, only areas or regions where they are likely to be.